In this session, we will look at some important random variables. Now, there are infinitely many random variables. In this course, we're going to try and look at what we think are the most important ones. So, one of these is the discrete random variable. We've actually sort of considered this already. In this case, if you have a discrete random variable, it means that the probability for every allowed value of the random variable x is the same. The probability mass function takes the same value for all allowed values of x, and it's 0 for all other values. So here's an example. Let's say we're going to toss a coin. The random variable x we'll say is 1 if you tossed a coin and got an H, and 0 if you flipped a tail. Okay, so the probability mass function, the PMF for this x, is 1/2 for x equals 0 and x equals 1, and it's 0 otherwise, right? So if x equals 0 means you got an H. Sorry, x equals 0 means you got a T, and the probability of getting a T is, for a fair coin is 1/2. X equals 1 means you got an H, and the probability for an H is also 1/2. And no other values are allowed, so the probability for any other value is 0. So here we have zeros for everything else, and the same constant probability for every allowed value of the random variable. Okay, so in such a case, we say that this x is a discrete uniform random variable. Okay, how about we have a fair die. X takes the value of the roll. So, oops, I made a mistake. You can't roll a 0. Okay, so take that out. So x takes the value of the roll. F sub x of x is equal to, what's the probability of the value of x being 1, 2, 3, 4, 5, 6? It's 1/6. What's the probability of x taking the value of anything else? 0. Okay, and so f sub x of x is equal to a constant for the allowed values, and it's 0 otherwise. Okay, so we call it, again, that's an example of a discrete random variable. Here's an example of not a discrete random variable. If you roll 2 die, x is the sum of the results, right? So you add the result of the one die and the result of the other die, you put them together, and x takes that value. The random variable x takes that value. Okay, it's not a uniform random variable, because if you work out what the probability mass function for x is, you'll see that it's not constant for every allowed value of x. Okay, so the discrete uniform random variable can be described this way, or the PMF. You have, it takes values x1, x2 up to xn with equal probability, and the probabilities have to sum to 1. That means that the PMF at x is going to be equal to 1 over n for x is equal to any of the allowed n values, and it's going to be 0 otherwise. So if we're tossing a single coin once, and x is the number of times that h results, then f of x is equal to 1/2, or x equals 0, 1, and it's 0 otherwise. Okay, so again, this is an example of a discrete uniform random variable, and it's equal to, here our what we call n is 2. Okay. Here, if you have x is equal, you have a roll of a die and you have to report the value of the roll, then X can take values 1, 2, 3, 4, 5, 6. They're all equally likely. It's a fair die. So the probability of taking any of these values is 1/6. And the probability of taking any other value is 0. Right? So this PMF has the form of a PMF for a discrete uniform random variable. Okay, what is the expectation for this? Right, it's recall that the expectation is of this x, then the summation I xi f of xi. Now the PMF is 1 over n. So if you have n allowed values with equal probability, then this is summation I xi 1 over n. N is a constant, so you can pull that out. So that's 1 over n summation I xi. So the expectation is the average of the allowed values that the random variable x can take, if they're all equal. Okay, so if you have a fair coin, then it would be the result is 0 times the PMF for 0 plus 1 times the PMF for 1 is 1/2. And that's the average of the two values that you can take for the discrete random variable x. Okay. What about the variance? The variance is equal to the summation of x squared. So the expectation of x squared minus the expectation of x quantity squared. And then this is equal to 1 over n summation xi squared minus 1 over n squared, the expectation. Remember, the expectation of x was summation xi times 1 over n, and then you're squaring that. So that's 1 over n squared times the summation of xi all squared. Okay. So let's see. Supposing, again, we're tossing a coin. X takes the value 1 if you get h, and it takes the value 0 if you get a tail. We've already established that this is a discrete random variable, uniform discrete random variable, and we know what the values we know the values of in the PMF. We've defined the PMF. So if we use this formula, okay, so it's you should be able to work out that the variance of this x is 1/4. So this part here is the expectation of x squared, and this part here is the 1/2 is being squared, the expectation of x. Okay, there's an analogous thing in the continuous case, the continuous uniform random variable, and this has this form. You have this random variable has a PDF f sub x, and that f sub x is constant on an interval, closed interval from a to b, and it's 0 outside the interval. The integral of a PDF from minus infinity to infinity should be equal to 1, right? Probability is all sum to 1. So the PDF has this form: f sub x of x is equal to 1 over b minus a for x from a to b, and it's equal to 0 otherwise. Okay, so this meets the conditions for a probability density function. You should check that. So what's the expectation? Expectation of x is the integral from minus infinity to infinity of x times the PDF for x. But this is going to be 0 outside the interval from a to b, so we only need to integrate from a to b. Integrate from a to b, x times the PMF on this interval from a to b has the form 1 over b minus a, and if we do that, we get a plus b over 2. Okay. So if x is uniformly distributed over a to b, then the expected value of x is the midpoint of the interval. And what's the variance? And the variance is equal to the expectation of x squared minus this quantity that we just found, a plus b over 2 squared. Right? So that's the integral from minus infinity to infinity of x squared times the PMF dx minus you square the expectation that you just found, that was a plus b over 2, and then you square that. Okay, now this PMF is 0 outside the interval from a to b, so we don't really need to. That's the only thing we need to integrate over. So we integrate from x equals a to x equals b, x squared times, what form does this have? It says the form 1 over b minus a. And then we do some standard integration, and we'll get 1/12 times a squared minus 2ab plus b squared. Next, the binomial random variable. I'm going to build up the PMF by going through examples and generalizing the examples as we go along, because I want you to see what all the terms mean rather than you just memorizing the formula. Okay. So you're going to toss a fair coin in the air 7 times and record the total number of heads that you get. Probability of getting an H in any toss is P equals 1/2. Probability of not getting an H, getting a tail, is Q is equal to 1 minus P. In this case, that's the same, 1/2. What's the probability of getting no H's? Okay. In order to get no H's and 7 flips, we need to get 7 tails. Each flip is independent, so you can multiply the probabilities of each individual flip. So you would get Q to the 7, which in this case is 1/2 to the 7. Okay. What is the probability of getting exactly this sequence? 1 H followed by 6 tails. Well, you have to get a probability H is equal to P. The probability of H is equal to P. Then again, all these flips are independent. So then you would get, you have to multiply by the probability of tail, which is Q times Q times Q times Q times Q times Q. Okay. So the probability of getting that exact sequence is P Q to the 6, which is 1/2 to the 7. What's the probability of getting this sequence? It's 1 H, but it isn't occurring in the first flip, it's occurring in the 5th flip. Okay, so what again, we're going to multiply the probabilities because the flips were independent of each other. Okay. So then the probability, so it's Q times Q times Q times Q times P times Q times Q. So that is Q to the 4th, then P times Q squared, that's P Q to the 6th. That's the same we had before, right? Okay. So how many sequences of heads and tails are there such that one element is an H and 6 are T? So basically what you need to do is you need to, out of 7 places where you could have an H, you have to choose one, right? And then you have its probability, right? And then you have to pick another one and another one and another one, and then you would add all those probabilities up. So how many ways are there to do that? There are 7 choose one ways to pick where the H is going to go. Okay, so 7 choose one ways to decide where to put the H. Now if we add up all of those, we would get the probability of one H in a sequence of 7 flips whichever position. So when we add up all the probabilities, right, the probability in 7 flips of getting one flip which gives us an H in any position, well, there are 7 of those, so it's 7 choose 1 p q to the 6. Okay, let's look at another one. What's the probability of getting 2 H's and 5 T's? Well, first let's consider the probability of getting H, H, and then 5 T's. What would that be? Right, these are independent flips, so we can just multiply the probabilities, right? So that would be p times, so that would be p squared times q to the 5. Now, how do you decide? And now we want to add up all the probabilities which meet this general requirement that there should be 2 H's and 5 T's. Well, how many ways are there to do it? Well, basically, you have to pick the 2 places where you have to choose the 2 places out of 7 to place the H, right? So there are 7 choose 2 ways of writing out the sequence of H's and T's which meets our requirement. And the probability of each one of those is p squared q to the 5. So the probability that we want when we sum up all the probabilities is 7 choose 2 p squared q to the 5. Okay, now let's generalize this a little bit. We could have, presumably we could have 0 H's, 1 H, 2 H's, 3 H's, 4 H's, 5 H's, 6 H's, and 7 H's. So let's generalize this a little bit and say we're going to get k H's. And we're going to get 7 minus k T's, right? And k can range any integer between 0 and 7. Okay, so we're going to get k H's and then 7 minus k T's. The probability of each one of these is p to the k times q to the 7 minus k. And how many arrangements like this are there, right? When I can put the H's wherever and the T's wherever, but I have to have a sequence which has k H's and 7 minus k T's. How many of those are there? Well, you have to, out of 7 places open to you, you have to pick k places where you can put your H's. So this is 7 choose k times p to the k q to the 7 minus k is the probability of getting k H's and 7 minus k T's in a sequence of 7 flips. All right, so now let's generalize from 7. You're going to toss the same fair coin n times and record a total number of H's. The probability of getting an H in any toss is p equals 1/2, and the probability of not getting an H in any toss is q is equal to 1 minus p. 1/2, it's the same in this case. Okay. What's the probability of getting an H for k times and a T for n minus k times? well, think of this. Think of a sequence which has k h's and then n minus k t's. What's its probability? It's p to the k times q to the n minus k. Now, if you can now have rearrangements of these h's and t's, how many are there? There are n choose k such arrangements. Right? They all have the same equal likely probability, right? Because of we get the probabilities by multiplying them because the flips are independent. Okay, so the probability of this particular sequence is p to the k, q to the n minus k. There are equally all the other sequences with k h's and n minus k t's have the same probability. How many such sequences are there? There are n choose k of them. So the probability that you toss a coin n times and you get k h's, with the probability of getting an h is p and the probability of getting a t is q, is n choose k, p to the k, q to the n minus k. Okay, generalizing again. Now, we don't have h's and t's are one example. We could have something that we label a success and something that we label a failure, right? When there are two possible outcomes, call one of them success and one of them failure. Okay. And there's a given probability for success, and 1 minus that is q is 1 minus p is the probability then for failure. When you have exactly two outcomes, one of which you can, well, we just call success, the other we call failure. Right, so for example, we might want to induce a disease in a lab rat. We stick a needle in and we try and do that. Not every lab rat will get the disease every time, right? So inducing the disease might be called the success, and not inducing the disease might be called the failure. Okay, and we might want to know, before we go ordering lab rats, we might want to know roughly, you know, if I order this many, then and the probability of inducing the disease in any particular case is this much, then this will give us an idea of how many of these lab rats we need. Okay, so we generalize a bit now. We're not going to call things H and T. We're going to call them successes and failures. So the probability of getting a success in any given trial is P, and the probability of getting a failure is Q is equal to 1 minus P. We're assuming that P does not change from trial to trial. Each trial is independent, like tosses of a coin. The random variable you are interested in is the total number of successes. Okay. So what is the probability of getting exactly k successes in n trials? Well, think of k successes followed by n minus k failures. What's the probability of that? Each of the trials is independent. So that would be p to the k times q to the n minus k for that particular sequence. Now, because the trials are independent, any other sequence which has k successes and n trials and n minus k failures, that would have the exact same probability of p to the k times q to the n minus k. Now, how many sequences are there that meet our requirement. Well, basically what you have to do is out of n trials, you have to pick k trials in which to write in a success. So now we want to add up all of these. How many of those are there? There are n choose k of those. So now if we want to write up we want to sum up the probabilities for all of the sequences that meet our requirement, then that would be n choose k times p to the k times q to the n minus k. So n choose k, p to the k, q to the n minus k. All right. So now we go on to a related topic, is the Bernoulli process and the binomial distribution. Okay, so Bernoulli process is, as we've been discussing, you have n repeated trials. Each trial results in a success or a failure. The probability of success P remains constant, and the trials are independent. Okay, so for example, you toss a coin 3 times, you see how many times you get an H. You might think of H as success and T as failure. Okay, so X is the number of successes, and the Bernoulli random variable is the number of successes in n Bernoulli trials. Okay, and this is characterized by, its PMF should be characterized by K is the number of successes that you get, N is the total number of trials, and P is the, in any given trial, P is the probability of getting a success. Okay, so K successes in N trials implies N minus K failures. The probability, the trials are independent, so the probability of a specific sequence of K successes and N minus K failures, that's P to the K, Q to the N minus K. And the number of ways to get K successes in N trials is N choose K. And so therefore, the PMF for the binomial distribution is N choose K, P to the K, Q to the N minus K. K can take integer values 0, 1, 2 up to N, and Q is 1 minus P. P is the probability of a success. Okay, so if we were to plot this on a graph, then it increases the probability of X taking the value K increases monotonically, and it decreases monotonically. And the point of the largest value is when K is the largest integer, less than or equal to N plus 1 times P. So here's an example. A doctor performs a surgical procedure with a 30% chance of success. Okay. What is the probability that there will be exactly 1 success out of the next 10 surgeries? Okay, so what's the probability? Here our P is equal to 0.3. Q is equal to 1 minus 0.3 is 0.7. Okay, so what would be the probability of a success followed by 9 failures? Well, the results of the surgeries are independent, so we can just multiply the probabilities. So it would be 0.3 to the 1 times 0.7 to the 9. Now, how many sequences are there? How many sequences are there where you have exactly 1 success and 9 failures? Well, 10 choose 1. you have to choose one of the surgeries in which you have a success, and then all the rest are failures. So the probability that you're looking for is 10 choose 1, 0.3 to the 1, 0.7 to the 9. Okay. What's the probability of more than 7 successes in the next 10 surgeries? Well, you break that into cases, right? So it would be the probability of 8 surgeries successful plus the probability of exactly 9 surgeries successful plus the probability of exactly 10 surgeries successful. So for 8, it's 10 choose 8. 8 surgeries are successful. Probability of success is 0.3, so 0.3 to the 8. And then 0.7 squared. This 2 is for the 2 trials in which you didn't have a success. The 2 surgeries in which you didn't have a success. The next one then would be 9 surgeries completely successful as well, 10 choose 9. You have to pick 9 places in which to put your successes. And then the probability of 9 successes is 0.309, and the probability of 1 failure is 0.721. And then for 10 choose 10, 0.3 to the, sorry, that shouldn't be 1, that should be 10, 0.3 to the 10. This should be a superscript 10 here. At times 0.720. Okay, so whatever that works out to be. As an exercise, you should show that the probability of 0 successes is 0.0028. Okay. Let's look at another example. You have a multiple choice exam with 3 possible answers for each of the 5 questions. What is the probability that student will get 4 or more correct answers just by guessing? Okay, so again, I would like to break that. I think I would probably want to break that up into cases. What's the probability of getting 4 successes? And what's the probability plus the probability of getting 5 successes? Okay. So you're going to do random guessing. So that means the probability of guessing any one question. So there's 5 trials here. On each one, you're going to guess. And it guess randomly. So there's 3 questions each. So if you're guessing randomly, the probability of getting that right is 1/3. P is equal to 1/3. And the probability of a failure is 1 minus P is equal to 2/3. Okay, so the probability of getting exactly 4 correct is, to get 4 correct, it's P to the 4th, Q to the 1, and there are 5 questions, and you're going to choose 4 to get to correct. So it's 5 choose 4 times P to the 4 times Q to the 1, which gets you to 10 over 3 to the 5. The probability of exactly 5 successes, well, the probability of 5 in a row is P to the 5, and then necessarily Q to the 0. And then you have to take, you have 5 questions, and you have to pick 5 of them in which to put your success. So 5 choose 5. Okay, so then you get 1 over 3 to the 5. And you add all of those together. You add those 2 things together to meet your requirements. And then that looks like 11 over 243. The company knows that the widget it produces will be defective with probability 0.01, independent of each other. It sells widgets in packages of 10, and it offers a money back guarantee that at most 1 out of 10 is defective. What proportion of packages sold must the company replace? I'll leave that as a question for you to test yourself. The answer is 0.04. Okay. What is the expectation of the binomial random? Whenever we have a random variable, we would like to know its expectation. We would like to know its variance. We might actually want to know more information, but at a minimum, I would like to know its expectation and its variance. Okay, so to take the expectation of a binomial random variable, well, what's in general, it's a summation over x over all allowed values x times the PMF for x. And in this case, binomial random variable, it has these parameters n and p, with x going 0, 1, 2 up to n. And then, well, there's this long derivation, and you should all work through it once in your life, right? But I don't want to just talk at you. So anyways, the expectation for the binomial random variable is n times p. So for example, if you flip a coin 100 times and you consider getting an H your success, and your binomial random variable x is the number of H's that you get, then the expectation for that x is n, 100, times p. Let's say it was a fair coin. N times 0.5 is 50. Okay. Now the variance, again, I've given you the reference for this, or you can follow through in the notes, and it kind of goes on and on. So finally we get the expectation of x squared is n squared p squared minus np squared plus np. Okay. And so that's the expectation of x squared, and we subtract off this expectation of x and we square it, that we found before, and then finally we get to the variance is npq. Okay. So we go back to the surgery example, 30% success rate. We're going to have 10 surgeries. The expectation is 3 is successful, right? N times P, we expect 3 surgeries to successful, kind of makes intuitive sense. The variance is NP times Q. So N times P times Q is 2.1, which gives a standard deviation of 1.45. Okay, so we're going to cover a number of random variables which are very important and come up with all sorts of come up in all sorts of applications. We've sort of just started that, but like I said, whenever you're given a random variable, the 2 pieces of information you really want to know about it are its expectation and its variance.